Okay, so let's start this second part of our session on life science and other societal challenges. We have a talk now from Professor Carlo Fiorini, a gamma ray detection module for BNCT dose measurements.
Thank you very much, and let me start first to thank the organizer for the opportunity to present this work at this conference. This is the outline of my talk. I will shortly recall the boron-neutron capture therapy for those who are maybe not too familiar with this technique, and also the possibility for dose estimation by measuring gamma rays. I will then describe a prototype of detector and related electronics that we have developed for this technique. I will show you then some first measurement of boron concentration with the instruments, and also preliminary test of position sensitivity, and then at the end I will draw future direction for the activity. Boron-neutron capture therapy is a different technique with respect to the more conventional radiation therapy based on photons and charged particles, in the sense that the tissues are irradiated directly by neutron, but prior to them, the tissues, they are loaded with boron compounds, which are selectively absorbed by cancer cells. Then there is the irradiation with the neutrons, and thanks to the presence of boron-10, which is an isotope of boron, there is a neutron capture, which generates particles like lithium and alpha, which release energies in the cancer cells, likely destroying them, but sparing the normal cells. So this is the basic of the technique, which is quite interesting, especially in some types of tumors like recurrent and metastatic tumors, especially in the head and neck region. This technique has been already experienced a long time ago, and but it was basically using neutron flux available from nuclear reactors. More recently, the technique has somehow became more actual because of the availability of accelerator-based neutron source, which are now available also from companies, and there are already clinical plants operational, especially in Japan, but also one in Europe, in Finland, and I would like also to mention the fact that also in Italy there is an agreement between CNAO in Pavia and Thai Life Science, which will bring the installation of a tandem accelerator probably beyond 2023. As in other techniques, there is an interest in those measurement, and in this case, the possibility is done by the fact that the neutron capture by boron release, in addition to lithium and alpha, also a gamma ray of 478 keV. And so the detection of such a gamma ray may open the possibility to monitoring the dose actually of the capture which happened in the tissue. This is also not a new idea, it's been already proposed time ago. You see, for instance, this reference of 2000, where this Japanese group proposed a SPECT system to measure the gamma rays emitted during boron capture therapy. These are the main specifications for the detector. Of course, it has to have a good efficiency for such energy, but also together with a good energy resolution to separe the 478 kV line from the nearby 511 kV coming from annihilation from a cascade of pair creation from gamma rays of higher energy due to other captures by oxygen, hydrogen, and so on. The spatial resolution is a target to be between 5 and 10 millimeter, expected to be limited by the collimator. And possibly a detector should extend the efficiency also up to 2.2 MeV, which is the gamma ray generated by the hydrogen capture, in order to have the possibility also to estimate the neutron flux in the tissue of the patient. In our team, we started a development for a detector to cope with this application. The detector is called Benedict and is basically a classical, almost classical scintillation detector based on a large crystal of lanthanum bromide read out by arrays of silicon photomultipliers and then read out by a custom electronics. The characteristic of the lanthanum bromide scintillator is to provide a very good energy resolution, better than 3% at 662 kV. And concerning the silicon photomultipliers, we are using the NUVAC D CPM from FBK with a pixel size of 6 × 6 square millimeter and a cell size of 30 micron, and we have also a version with 15 micron. And then the system is equipped with the electronics, which is summarized here. The core of the electronics is a readout Asic called Gamma, developed in our team, where we read out the current from the CPM. We integrated in a gated integrator, and then we provided the pulse to an external ADC, which is controlled by an FPGA, and the board include also microcontroller for gain stabilization of the CPMs with respect to temperature. Just a few words more about the Gamma Asic. It's an Asic that we developed specifically for gamma rays. It provides mainly two features. One is compatible with the largest IPMs, even with several tens of femtofarad of capacitance, and also is equipped by an adaptive gain control, which provide a very high dynamic range, so from few photons up to more than 10,000 photons. So this is implemented by an active switching, which set more capacitors in parallel to the integrator. You see here the different gains for low noise and high gain, and then low gain. And this is automatically set by the chip with a predictive time system. You see here there are two thresholds, one threshold and two time windows. So when the signal is small and the output is not crossing the threshold in the windows, the amplifier is let to go. On the other case, if it crosses the threshold in the second window, we switch automatically to the middle gain, and if the signal is large, we switch to the other gain. This is a typical energy resolution of the detector. It's 2.7%, which somehow projected to the interesting line of 478 kV, open the possibility to distinguish this line from the 511 kV. Of course, this is on paper. So we then made some specific measurement at the nuclear reactor in Pavia, in Italy, where we made some irradiation with a neutron beam on vials containing boron-10, including boron-10, at different concentration, and we checked out the possibility to detect the energy and to check the sensitivity with respect to the boron concentration. You see here the instrument not yet shielded, and then you see the instrument shielded with cadmium foils in order to reduce the effect of the neutron background. Thank you. This is the result of the spectroscopy measurement in the test. You see here that actually it's possible to distinguish the boron line with the annihilation line. You see here better in the zoom. And in addition to these lines, you see other lines due to the neutron capture by the cadmium shield. And also you see that there is a possibility here to detect also the 2.2 MeV capture photon from the hydrogen. This is the result of the measurement at different boron concentration. So these are in the horizontal scale the samples boron concentration, and these are the counts per second recorded by the instrument. The two lines, the one on the bottom is the vial alone, and the second one is the vial but inserted in a water phantom. You see that in both cases there is a good linearity with respect to the detected signal and the concentration of boron. You can observe that both plots do not go to zero for zero concentration of boron, and this is due to some background, some counts in the interesting region due to most probably activation of the detector or components of the detector by neutrons, and this is a topic that we need to start to investigate, but nevertheless the lowest concentration we could detect is 62 ppm of boron, which is I would say not far from what is expected in the final application. Then we change the configuration in the detector, because so far we did just spectroscopy. Then we removed the crystal and we substituted with a crystal with a square geometry, more suitable for imaging. You see the size is 5 centimeter and the thickness is still 2 centimeter to get a reasonable detection efficiency for the interesting line. The resolution is still good, in the order of 3%. And with this detector in laboratory, we start to assess some intrinsic position sensitivity by scanning the detector with a collimated source of cesium-137 with a photon beam collimated to 1 millimeter. It was possible to scan the detector. You observe that the energy is far from the one of boron-neutron capture, but this is a starting point with an apparatus we had in the lab, and then in the future we could repeat the measurement with the right energy. So what we have done, we have made a scan here, you see, of the surface of the detector with the points separated by 3.11 millimeter, and then we used this database to train a machine learning network in order to then make a test of a classification of these positions. The network we have implemented is a convolutional neural network. So the input of the network is the pattern of the 64 SIPM signals. You see an example here. And then the output of the network is the predicted position we should have generated such irradiation. So we have first made the training, then we have made the test with another set of data. And you see here two examples of outcome. The true prediction, when actually the predicted position is the one actually correct, and then false prediction when the outcome is not the true position. So making this test, we were able, as done in these cases, to build a confusion matrix. This is related to the X coordinate. With the horizontal axis, there is the predicted classes by the network, and in the vertical axis, the true classes. So this matrix should be diagonal. This is not true, of course, but the average accuracy is 65%, and if you add the neighbor pixel with respect to the correct one, the accuracy increases to 90%. And a similar result is available for the other coordinate. So maybe this can be also seen in a more traditional way. This is an image, a reconstructed image of 2 points separated by about 16 millimeter, and you see the reconstruction position with a full width of maximum of 3.6 millimeter. So this was just a measurement to assess the intrinsic position resolution. So this is what has been done so far. Regarding the future, we want to continue, and in particular, we want to continue to prepare imaging tests, in this case, using boron 10 samples and developing a suitable collimator. The study of the detector shielding is very important in order to increase the sensitivity to lower boron concentration. I did not talk about but we also started a collaboration with ANSTO in Australia for somehow related technique, which is in chapter, is neutron capture enhanced particle therapy. So this is a technique based on more conventional proton and carbon therapy, where the neutron are the product of the interaction of proton and carbon in the tissues. And so then by loading the tissues with boron, these neutrons created by protons may enhance the therapeutic effect. If you want to know more about that, we have published recently with this collaboration, this paper. And finally, regarding our hardware, we are quite interested in implementing machine learning techniques for the reconstruction of position of interaction, and in particular, we are looking to possibility to design hardware accelerators, and in particular we are working also about a possible dream to implement an analog neural network directly in the Readout Asic. So that's all for the presentation, and I thank you very much for your attention.
Okay, thank you very much for this really interesting talk. There's one question there. Is it possible to, sorry. Okay, please, yes.
Thank you very much for a terrific talk. I wanted to ask, regarding your use of a convolutional neural network for finding your most likely point of incidence, what is the advantage of using a CNN over traditional peak fitting algorithms? Is it faster? Or?
It provides a better linearity, so please consider that this is a quite a thick crystals with respect to the size. So if you would traditional centroid algorithm, you would have the image squeezed toward the center. So in this case, the network can train this feature and can provide you back a reasonable imaging even in this extreme case.
Thank you very much.
There was another talk there, yes. Another question there, yes.
Thank you, Carlo, for the nice talk. My question is, how do you calibrate the 3 gains of your front-end stage? And did you also consider other high dynamic range architectures? Thank you.
No, so we calibrate by using an optical emulator. So we have a laser which is pulsing light. So we expose our SIPM matrix so we can make the full photon range, and we calibrate the system. We did not consider other solution because this solution, in my opinion, is very nice. We did not invent it. It was proposed by in a chip in Trieste, I think, and also many chips in the X-ray domain, as you know. And we think that it works very well also for SIPMs because you can get from few photons up to 10,000 photons, and so that's the reason we are fine with that.
Thank you, Carlo. Very interesting talk. I think it was just a curiosity, slide 12, if I remember well. The error bars that you have in your points are just statistics here?
Yes. Just statistic out of 15 minutes of measurement for each point.
Okay. More questions? No? If not, we thank the speaker again.
So, and the next talk is from Michael Lupberger, Particle Physics, Readout Electronics, and Novel Detector Technologies for Neutron Science. Welcome, Michael.
Give me a second.
Yeah, so you're fully connected.
Okay, yes, as I was introduced kindly, this talk will be about technology transfer from our field of particle physics into neutron science. And in my outline, I'm just going through what I will tell you. So first of all, I will explain you a bit how neutron detection works. I will then tell you about the requirements of novel neutron detectors, and then go through 3 technologies which we apply from our field of particle physics into neutron science. And I hope in the end of the presentation, you are able to understand these drawings here. Okay, so why we need neutron science? I think, especially in this country, we know that making good coffee is an art, but for us, this is not enough, so we want to make science out of it. And this is one of the main reasons why we need neutron detectors, I think, beside of a few other applications. Okay, so in this image that I have shown you, a mocha cup, you have probably seen that the metal parts were more or less transparent. And this is due to the fact that neutrons, in contrast to X-rays, where we are more familiar with, they hardly interact with the iron, but they mainly interact with hydrogen-containing elements. So this is why you have seen the coffee as an organic material or the water in the mocha pot. Another image which illustrates this quite nicely is this Buddha statue. You see the visible image here, the X-ray image, where you see in absorption imaging the metal parts. And then for a long time, people were not knowing how these statues were made. And with neutron absorption imaging, we were able to see inside. And for example, see this wooden stick here, which basically holds the structure, and also some other organic material here at the bottom. So neutrons mainly interact with water and with other organic materials. And what is also interesting, they interact with the hydrogen atoms at the border of the molecules. So for example, if you have a pharmaceutical drug, the hydrogen around it is what interacts with your body, and to get to know where those are, it's interesting to detect the neutrons, to scatter them at the atom or at the molecules, and then get a hint of where these atoms are in the molecule, in the medical drug. Okay, so this was only what can be detected with neutron, but how do we finally then detect neutrons in our detectors? And what we do there is, the enabler is basically the conversion of the neutron to a charged particle. And for a long time, helium-3 was used as the main detector material in neutron science, because what's nice here about helium-3 is it interacts with a neutron, and we get a charged particle, a proton out. And neutrons, in my talk, are in contrast to the talks in the morning, not in the MeV energy range, but more in the micro or milli-electron range. So they are thermal, they have wavelengths in the range of the atoms. This is why we can also inspect the molecules with them. So they travel at around 1,000 kilometers per second, so comparably slow. So what you see, what happens in a neutron helium-3 tube is the neutron interacts with the helium atom, and you get this proton out. The proton ionizes your gas. You can capture the charge with this wire, and then you can build arrays like a straw tube detector, we would call it. This is just helium-3 tube to get the scattering image of a neutron beam that goes to a target here, and you get the diffraction image then at your straw tube detector. When we go into the future, we have a big project that is currently being built in Lund, the European Spallation Source, where there is harder requirements for neutron detectors. So you see the requirement for spatial resolution here, needs to be improved by a factor of about 4 or 5, and the area has to be also increased for, depending on your application, not too much at all, but sometimes also a factor of 2. And this all implies that you basically need a factor of 10 more readout channels. What is even more severe, because of the high brilliance of the European spallation source, the rate at which the neutrons come is rising significantly by an order of magnitude for certain instruments. And all these 2 basically implies that we have to go away from discrete electronics into integrated electronics, and this is basically a field where we are, in particle physics, very familiar with. Another thing which hit the neutron science is the so-called Helium-3 crisis. So you see the available amount of helium-3 in the Earth stock, and helium-3 is mainly coming from the tritium in the nuclear weapon stockpipe, and happily the stockpipe is significantly reduced. That's a good thing, but we lack helium-3 because of that, and in addition, because of 9/11, for homeland security, most of the helium-3 stock was actually bought off by the US. So for the European spallation source, there was really the need to go further with technology, and there was the search for new neutron converters, and there is basically the way was to go to solid converters, as we heard in the previous talk, for example, the boron-10. So here are a few materials that are interesting, and the requirements that we need for neutron detectors. So we want to have obviously a high absorption cross-section to stop the neutron and detect it. We want to have charged particles, because those we are familiar with to detect, and we want a material that can be easily handled during the construction. There are a few elements in here, for example, uranium, which we possibly don't want to use when constructing a detector. Lithium is also difficult. Gadolinium, if you look at the cross-section, is extremely nice, but there is an electron ejected when the neutron converts, and this makes the detection really, really difficult, because usually whenever you have a neutron beam, there are also a lot of gammas coming, and the gammas do Compton interaction with your detector material, and the Compton electron basically looks the same as this electron that comes from the neutron conversion in gadolinium. There are detectors which use this, but it's challenging. And so we decided for ourselves that we will use boron-10. It has a cross-section which is comparable to helium-3, so we get sensitivities in the same range as we are used with our helium-3 tubes, and it's easy to handle. So that's why the detectors I will show you in the future, in this previous slides, are based on boron-10. Okay, and now I will come into the 3 detector prototypes we are building. This first one is a microchannel plate with a Timepic-3 readout. So the microchannel plate basically is it's a plate with fine pores. You can see it here or there. They are slightly tilted. You apply a high voltage between top and bottom side, and basically it's a highly integrated photomultiplier tube. So a neutron comes, hits a boron, which we load into this material here. It emits 2 particles, the lithium and the helium core here. They interact with the walls here in the photomultiplier tube, or in the, PMT. And there are electrons ejected, which are then hitting the wall again because of the tilt and the electric field. And basically what you get out at the bottom is an electron cloud, which you then need to capture. And you put just a charge-sensitive device there. And in our case, it's the Timepic-3 chip, the bare Timepic-3 chip. So we use the bump bond pads of the chip to collect the charge. And so this is how the concept works. You have a neutron beam, the objects you want to evaluate, scattering, absorptions, whatsoever. And then we put the detector behind. There's a window. Because all this is in vacuum, microchannel plates need a vacuum to operate them. So we have the boron or gadolinium loaded microchannel plate here, and behind the Timepic-3 chip. In our case, we want to put 4 of them to just increase the sensitive area. So this comes also with some requirements. I told you already we need a good vacuum to operate the MCP. All the vacuum parts have to be constructed from aluminum because we don't want to activate our material. And aluminum has a very low cross-section for neutrons, so it doesn't activate. The Timepic-3 has to be very close to the MCP to really capture the charge. And we need to cool within the vacuum. And on this slide, you see now how it works. So this is the drawing. You see again, as before, quartz window, MCP, Timepics. And then, this is the vacuum flange at the backside, which is directly connected to the Timepic-3 Asic. And this is how it looks in reality. At that time, not with the real MCP, but just with the plate there to do the high voltage tests. And the detector, well, it looks large, but the sensitive area is just this one. The main part goes into the vacuum system. A word on the readout. So there was actually some work done before by colleagues here, where they did in principle the same concept with the TimePix chip, but the TimePix chip is a shutter-based readout, so there was a large dead time. And well, we just picked up this concept and put the TimePix 3 there, because it has nice features that, well, you can measure charge and time of arrival simultaneously. You can get a good time resolution, and in particular, this data-driven, self-triggered readout. So with this detector, we really have a high-rate capable, really high-resolution, spatial resolution neutron detector. And if you go to this work, so we implemented the TimePix 3 in the general readout system of the gaseous detector community, RD51. Not only because of this project, but just for a few other projects where we apply the TimePix 3. Okay, the next detector I would like to show you is a time projection chamber with GridPix readout. So here we see just, well, time projection chamber as we know it. We have the cathode, we have the gas volume here with an electric field, and the anode at the bottom. But when we look a bit more into the details, we see that the walls here, they are coated with boron-10. So when a neutron comes, it will eject the two particles, and now we take really advantage of the two particles because one will eventually enter the gas volume and make a track in our TPC, so this is what we know. But usually the problem in the TPC is that we don't have a time reference, so we need a T0 signal that usually in our particle physics detector come from other detector or subdetector systems. But here we can take advantage of the second particle, which goes in the other direction, and we just put a scintillator there and wavelength shifting fibers and the silicon photomultiplier to use this as our self-triggering, as the time reference, to then reconstruct the Z position of the neutron in the detector. So this all then, the light goes to silicon photomultiplier array here, that then goes to a trigger board, and this trigger board basically then puts the T0 information into the stream of our streaming TimePix 3 readout. And I don't write TimePix 3 here, but I write GridPix. This I will come to in a few slides. This is how it looks like at the moment. So you see the detector here at that point, not with the scintillating balls, but just as a standard particle physics time projection chamber. So we have wires for our field shaping here. And we were using this as in a cosmic setup. So we have scintillators now outside of our detectors to trigger. This is still with the TimePix 1 at that stage. And we can then just nicely see the tracks of cosmic muons in our array of 8 TimePix chips in this case. I was mentioning GridPix technology. So it's a gaseous detector technology that is basically a combination of micromegas and a bare pixel ASIC. So you see the two here. This is the micromegas concept. This is the pixel ASIC bump bond chips. And what we do is just by lithographic post-processing, we build the micromegas on top of our pixel chip here. So you can see the bump bond pads here. There's a protective layer to quench discharges in the gaseous detectors. Then we build the pillars and a micromegas mesh such that every hole of this mesh is exactly above one of those pixels. So when a primary electron from deionization enters this hole, we get a signal on just one pixel, and by this we can in principle do single electron counting and do tracking, for example, and this is what we use in this setup here. This concept, the GridPix, is employed in several detectors. So, for example, in the detector for CAST experiment, it was proposed for the ILD TPC at the ILC, for the Athena TPC at ELC, for YAXO, and as I learned yesterday, also for the TPC upgrade for Bell 2 or 3 or whatsoever. So that's really nice. Okay, so the last detector concept I would like to show you is a gas electron demultiplier combined with the VMM3A ASIC. So this is the concept. There is already a detector, the Cascade Detector, which uses gems in multi-layers with boron, and we want to somehow improve this concept by, I cannot go too much into detail because we're just on the way to patent this concept, but basically you have highly segmented gems here, boronated, such that you then have XY strip detector, gaseous strip detector, as you possibly have seen it for compass, for example. So this was the first gem detector employed at a running large physics experiment 20 years ago, compass large area gems. And if you look at our neutron detector, it basically looks the same. You have the front-end electronics outside. In this case, it's the VMM3A. Here it was the APV chip. Okay, a word on the readout here as well. So the VMM3A ASIC was also implemented in the scalable readout system. I go a bit more into detail because this readout system will actually be the workhorse for the gaseous detector community in particle physics in the next decade. So we have our front-end boards here. You have seen them previously. There are 2 VMM chips here. There's an FPGA which combines the data and controls the 2 chips. And then you put the data upstream to your main working board here, the front-end concentrator board with the main FPGA, and then you go into your computer via an Ethernet switch, for example. So you can make crates like this. It's a star-like architecture. It's scalable from just a single of these front-end boards until, well, 60,000 detector channels. Okay, so I'm coming to my summary now. I hope I have shown you that basically the state-of-the-art neutron detectors is just taking your particle physics detector concept, combine it with a solid converter, and put some recent particle physics front-end electronics. Well, it's not as easy as it sounds, but pretty much that's the concept. So I have shown you 3 of our concepts. Here is the microchannel plate combined with the Timepic3, the time projection chamber combined with the grid picks, and the gem detector combined with the VMM readout. And yeah, this is the technology transfer that we do from particle physics to neutron science. And we have the 3 novel concepts developed in Bonn, all for completely different requirements. So here we have high rate, small area. Here we have large area with not so much, so high rate. Yeah, here we have this special TPC concept with timing capabilities slightly. And yeah, they all fulfill different requirements. Yeah, and with this, I thank you for your attention, and your applause should not only go to me, but for the people who actually do the work.
Thank you, Michael. So we have time for a very quick, urgent question. So over there, the very quick, urgent question. Yeah. So can you? Yeah.
Thanks. Can you go to slide 8 quickly, or I can just describe it? I wanted to ask about your choice of converter here, because it says on your slide that you have the width of the columns is 10 microns, and I'm just wondering how often you actually see a lithium-7. You know, if it's produced in the center of the column, I'm guessing it doesn't get to the edge.
Yeah, that's
whether that could affect your choice of converter.
That's the thing. I'm not too sure whether we will employ exactly the dimensions that are displayed here. So that's always the problem when you come to neutron conversion, that your converter thickness is basically, or you want to have a thick converter to absorb a lot of neutrons, but you also have to extract the charged particles. So here you have to come to a trade-off. I cannot really answer your question. So typically,
I suppose a follow-up could be: are you able to make these MCPs with say a lithium compound inside? Because then you would have particles that would travel, would have greater range, basically.
Yeah.
I know, but I'm saying if
you would like to implement lithium, as I understand, because you have a longer reach of your particle.
Correct. Yeah.
Yeah. Thanks.
So thank you, Michel. So we thank the speaker again, and for more questions, you can discuss also. So
we move to the next talk from Kaplan Lucas, from JPET prototype to total body PET scanner.
Good afternoon. I will talk about development of our novel position emission tomography. First, I will talk about motivation. Then I will present principle of operation of our detector. Okay. And then I will show first Jagiellonian position emission tomography prototypes. Then I will talk about the concept of total body PET scanner. And then I will show first in vitro positronium imaging did in our detector and some conclusion at the end. So motivation of our group is to build cost-effective total body PET scanner based on plastic scintillators, because traditionally in hospital PET scanners are based on lysocrystal, some inorganic scintillators. And we also built PET scanner with positronium and multiphoton imaging capabilities. And our scanner is also modular and transportable to adjust field of view to the patient, for example, and other physics experiments. So principle of operation is that our scanner is made of long plastic scintillator strips, read out by photomultipliers at the both ends, and if the gamma interaction hits plastic scintillators of both sides, we read timing of signals from both, and if you have interaction point with 1 and second strip, you have line of response, and applying some cuts and timing on electronics, you can adjust position of emission of this gamma quanta. Here on the right is example of a voltage signal from photomultipliers if the interaction is close to one photo detector in the middle and on the right. And to suppress some low interaction photons, we sampling our signals with 4 threshold on leading edge and 4 threshold on trailing edge. We sum these thresholds, and we use time over threshold technique to distinguish, for example, back-to-back 511 keV gamma quanta from background or other scatters, and also some prompt gamma for example, sodium-22 isotope. And more information about data acquisition system will be given in poster session on Friday at afternoon. And main difference between traditional PET scanners and our Jagiellonian PET scanners is that we are making based on plastics, and we are interacting Compton scatterings to detect gamma quanta, because scintillators have lower density, but they have excellent timing resolution, and also the light attenuation in the strip is order of magnitude higher than in inorganic crystals. And we have very high acceptance of, because our detector fuse prototype is half meter long, and in hospital PET is about 20-25 centimeters, and we are also able to detect simultaneously whole body imaging or insert our detector to MRI scanner or CT scanner. And you have also some comparison in lysocrystal in the 20 centimeter field of view, and in the black curve is gain in our detector if you use plastics. So we can adjust the length by making scintillators longer without cost of electronics and silicon photomultipliers, for example. And this is why it can be done, because scintillators have very light attenuation length. This is length that attenuate light by 1 over E. So we tested with some simple setup, exciting scintillators by multivariate lamp and reading on one side by photodiode and multimeter, and we tested all scintillator types that are available in the market, and the best one is BC408 and EG200. They possess the lowest attenuation light along the 1 meter strip. Here is some example. We also tested different cross sections, 6 mm by 25, 6 by 12, and 6 by 6. And in preliminary result, we have found that the best higher signal is by this 6 by 6 millimeter scintillators. So here is example of photographs of 2 scanners, so-called mini Jagiellonian positron emission tomography based on 24 scintillators and vacuum photomultiplier at the end. And in the newer version, modular JPET, we have replaced vacuum tube by silicon photomultipliers. This is enhanced specular reflective foil to reflect lights to the silicon photomultiplier at both ends. And we choose silicon photomultiplier because they have more compact, they have higher photon detection efficiency, also lower supply voltage. So this is timeline of our project. We started first in 2009 in international patent. Then we built a very simple two-strip setup. And by average 2-3 years, we built the bigger detector. Now we are build modular one with over 300 scintillators read out by silicon photomultiplier. And within a few years, we are going to make total body pad with field of view 2 meters, because this is half meter. And this is a close-up of our detectors. So up to date, these are operational fully. And this is recently built in the last year. So this is comparison of these detectors. We started from 2 pieces of scintillators, and gradually we moved to bigger number of scintillators, because in this second project it's air gap between scintillators, so we would like to cover as much detector as possible. And we also change photomultipliers to silicon detectors, and at the newest generation we have almost 2,500 light detectors, over 3,300 scintillators, and spatial resolution is around from 10 to 11 millimeters. And we are going to make resolution up to 240 picoseconds. So this is example of spatial resolution obtained by point-like source, and we have good resolution with X and Y, Z, but slightly lower with Z direction. That this is the length along the length of strip. So this is example how this modular detector one work. We can mount the individual module to aluminum frame, for example, and close it and image patient. So recently, in 1 or 2 months ago, we go to Medical University of Warsaw, and we image a real patient with injected radiopharmaceuticals along with commercial PET scanners in the time of 1 or 3 hours after injection. And we also did imaging of PMMA phantom irradiated with proton beams. So our detector can be assembled not only in barrel, but also with some rectangular shape aluminum for 2 left and right signal. This is data acquisition system and electronics. And this is example, this PMA phantom. This is proton beam irradiation, and we read out gamma that ejected from this plexi phantom. So on total body JPET design, the future version will be that 16 plastic scintillators will be glued to silicon photomultipliers at the end, and there will be 2 layers of these plastic scintillators, and between them there will be layer of wavelength shifting plastic to increase resolution along the Z direction. And this module will be assembled with some ring. 24 such module will form a ring. And then to extend field of view along Z, we will build 7 modules, 7 rings. And we use this wavelength shifter because we have slightly lower resolution along the Z. So the blue light emitted with scintillators is absorbed by WLS, and green light emitted with WLS is readout with one side from for photomultiplier, silicon also. And we use silicon photomultiplier because emission spectrum of plastic scintillators and green wavelength shifter is much or less at the maximum quantum efficiency of conversion for this type of detectors. And for future total body JPET, we have a huge sensitivity gain, because if patient is in the center of this detector and with 7 rings, so if you increase plastic scintillator's length, we can imagine standard so-called 2 gamma imaging, but we're also going to imaging multi-photons. So we did first in the world measurement of in vitro positron imaging, because part of the positron inside human body, if you inject radiopharmaceuticals, not only have direct annihilation to back-to-back gamma quanta, but also emit 3 gamma. And after we have performed such experiment that we place sodium source between 2 tissue, and we place 2 samples, 2 cancer samples and 2 healthy samples in our detector. And after analysis, we found that we can distinguish orthopositonium meal lifetime. This lifetime depends from porosity of the tissue. So the fast ortho mean lifetime, the dense tissue, and cancer tissue have very dense composition. So we can, for these 2 samples, they have higher dense, and the healthy tissue has higher this lifetime. And up to summary, we are developing a novel position emission tomography based on plastic scintillators that is modular and transportable. Now we have field of view of half meter, but after another prototype, we are going to build 2 meter per detector, and it's cost effective in comparison with other total body PET scanners, because we are targeting with about 4 million euro per 2 meter, and currently such scanner costs over 12 million euro, and we can image not only standard back-to-back gamma quanta, but also positonium and multi-photon isotopes labeled with biomolecules. Thank you for your attention.
Thank you very much for this interesting talk. Are there questions? Yes, please. There.
Hello. I have actually 2 questions. The first is, how do you distinguish the scattered photons in the body and in your detector? How do you compare your resolution with the state-of-the-art PETs?
So distinguishing between scatters is done by several cuts. We apply angular cuts, because this gamma quanta is back-to-back. Then we apply energy cuts, because some of this energy must be lower than some of the back-to-back quanta. And we also apply plane cuts, because these 3 gamma are in one plane. So we can distinguish by time over threshold technique. And about the resolution, so preliminary, we are targeting to this 200 picoseconds, but on the newer prototype, we have about 400, 500. So it's still a lot of to improve. The best PET commercial scanners have around 250 picoseconds resolution.
No, spatial resolution.
Spatial in millimeters. So now we have about 25 millimeter. but in hospital they are lower. So.
But in your table you mentioned 11, right?
Yeah, but it depends from this prototype, because we have built 4 prototypes, and there is vary because you change photomultiplier vacuum to silicon. It's slightly different, and we also change length of scintillators and type to match the best combination, and we have few examples of this resolution.
Okay, thank you.
Thank you very much. Then we thank the speaker again. And we move to the next talk.
So, we welcome Mateus Vicente Barredo Pinto.
Thank you.
Who will present us his talk on the 100 micropet project, an ultra-high resolution small animal PET scanner. So, you're settled up.
Thank you very much. It's not too loud. Hello? Yeah? Okay. First, thank you for the opportunity to show this new project that we have in Geneva University. So this project is, we aim to pioneer molecular imaging with ultra-high resolution. Okay, the deliverable will be a small animal PET scanner. Okay, made with monolithic silicon pixel detectors. This is the differential. Okay, it's a CNSF Synergia project with Geneva University. Okay, so Geneva University, and we will develop and construct the scanner. EPFL, which will be responsible for new imaging reconstruction techniques that will be required for this new type of PET scanner. And University of Lucerne, which they will do the medical application with this. Okay, so in the medical application, the plan is to study atherosclerosis in small mice. And the idea is that with the resolution that we will achieve, we're going to go from something like this that we have today, something like this that will allow us to measure this atherosclerotic plaques. So just a bit of introduction, what we are doing in Geneva University, especially with hybrid or monolithic pixel detectors. So we worked with the Atlas IBL, we built the IBL in Geneva University, we worked in the ITK upgrade, but also, for example, the SCT in Atlas, the AMS in ISS, and DUMP experiments. In 2015, we started the R&D on monolithic pixel sensors using the silicon germanium BCMOS technology to make monolithic detectors. And the idea of this R&D was to aim maps with timing resolution below 100 picoseconds. Okay, this for MIPS. And we are using the technology from IHP. So with this, we have a few projects. In fact, there are 2 posters and some talks that were presented recently. On the Monolith project, there is a poster, please have a look, and also on the phaser pre-shower detector. So this is a brief list of our prototypes. This is the most recent one where we get about 20 picoseconds timing resolution, a picture of it. And okay, so this is the team. We from Geneva University on this block here, and these are the people working on the PET scanner, the team from Lucerne and the team from EPFL, and also some other collaborators that you might know. So I don't think I need to explain PET once more. But the idea is that, okay, we measure the photons back to back, of course. We create the line of response. And this is a panoramic overview of the commercial PET scanners that we have around with the sensitivity or detection efficiency for the 2 photons and the volumetric spatial resolution, okay, in millimeters cube. And I think this should be updated with the new detectors that were presented here. So please, we're going to talk after. Very nice. So you see this goes from 50 to 0.5 millimeters cube, and efficiency is up to 10%. Okay. And our idea. So our idea is that to access ultra-high resolution, we're going to reduce the line of response volume or the volume of response. And this can be done by either having better timing resolution, doing the time of flight PET, or we can improve the depth of interaction measurement. But our idea is to improve the spatial resolution, increase the granularity of the sensor. And we're going to do this using the pixel detectors we have in the high-end community for the PET scanners. So for example, I try to illustrate here a conventional PET detector with the LISO crystals, with dimensions in the order of millimeters, okay? We get a sensor granularity of 320 millimeters cube. And the idea is that using a stack of pixel detectors, okay, monolithic pixel detectors, with, in this case, with 100 microns pixel pitch. The sensor would be 250 microns, but you have the flex, you have material, so let's say depth of interaction for 400 microns. We get a sensor granularity of 0.004 millimeters cube, okay? And the idea is that this will reduce so much the line of response that, for example, in this case, this is what I try to illustrate here. If you have this thicker line of response, for example, in 2D case, this line of response will have some ghost crossings where they should not happen. That could be indicated by, well, this will be some noise in your measurement, in your imaging. While if you have this very thin lines of response, this crosses doesn't happen. So the idea is that we're going to reduce noise-like combinatorics from the production of the lines of response. And we're going to have 80,000 times smaller line of response with this. So I said it's a new project, but in fact this started in 2016. 1 year after we started silicon germanium monolithic pixel detector R&D, and went up to 2019. Okay, we had time on this project to do the demonstrator chip. Okay, where we show here, it's hard to see, but you can see on the PDF. For MIPS, always 100% efficiency, or 99.9. The timing resolution that we have with this prototype was about 114 picoseconds. Okay, we did the engineering of the scanner. So as I said, this would be a monolithic pixel detector with a 500 microns pixel pitch. We would stack these pixels, the pixel detectors in modules. We would stack these modules. We're going to put them around cooling blocks, and then we would repeat this, I think, 16 times. Yeah, 16 times to put patient in the center. So again, this is small. Okay, this is for small mice. And here, for example, you see a prototyping. We did the stacked wire bonding for some test devices. So we did a lot of engineering here. But also we simulated the performance of the scanner with Gent 4. We did the imaging reconstruction technique, okay? And with this, with the point spread function that we measured, okay, I tried to summarize here on this table with the source being in different positions, but you don't need to understand this table. I can just show you, after crushing these numbers, where this would put us in the resolution, okay? So you see that we have a good improvement in the spatial resolution that we can achieve. You can see here the 0.5 millimeters sources of the Derianzo phantom, and with efficiency of about 5% for the 2 photons, okay? So a change of paradigm impact imaging is possible using monolithic pixel detectors, but can we do better? And to do better, we must reduce even more the line of response, the volume of response, okay? Again, either by pushing the timing resolution, for example, for the 30 picoseconds, that there is a challenge of to achieve this. But again, we can push more the spatial resolution. Okay, so simulation has shown that using 100 microns pixel pitch and the imaging reconstruction technique, a simple filter back projection, we can achieve 0.04 in spatial volumetric spatial resolution. Okay. Can we also increase the efficiency? So this is what this is more or less where the 100 micropads project starts. So what we did was to simplify and improve the scanner geometry, okay, and mainly by replacing the cooling blocks in acceptance of the scanner, okay, which before was accounted more or less for 25% of the scanner volume. So the Asic is different because we have a different pixel pitch. So we are planning to have a 2.5 by 3 centimeters, so a quite large Asic with the 100 microns pixel pitch, 250 microns of active silicon pixel pitch, so it will be fully depleted. And a module of this scanner will be a 2 by 2 chips covering 30 centimeters square. So again, this is for a small animal first. It's a proof of concept. And we would have 4 detection towers, okay? Each detection tower will be composed of 60 layers of silicon, and which give us about 1,000 chips on this very compact scanner. So it's quite a challenging thing to do. And as this is there is some challenge there with a large number of services and interconnections, we are investigating 2 possible designs. The first design, which is more or less the baseline design that we have now, would be 5 detection layers, so 5 silicon layers, each layer with 4 chips, so this would be 20 chips. stacked on a PCB, wire bonded, and we would have 12 of these to make the 60 silicon layers. Okay. Another approach that we start to do now, and this involves Acf bonding, so you can click on this link to understand more, will be a single detection layer, okay, still with 4 chips, but then we would have 60 of these plexes and silicon chips stacked together on a tower, and again, 4 towers around. And this has some advantages, because with this you can have the scanner smaller, so we increase the efficiency, the integration. We don't have very complicated wire bonds, so it's a new, how can I say, detection, integration, bonding, or interconnection using Acf bonding. So what are we doing? We are simulating this. We still don't have it, so, but okay, of course we can do simulations, and for simulations we are using Gent4 via our P squared, which helped us a lot to do this turnaround in simulation fast. And we start with a simplified case, okay, a single photon source, so not the photons back to back, ranging from 0 to 30 degrees, 3 millimeters from the tower, detection tower, in a single detection tower. So this is how it looks like. We have a cooling block, okay, we have then the silicon in the flex 60 times. This is how some events looks like. And we are doing this to get the photon detection efficiency, and also to calculate the distance of the line of response. So now we are not doing the imaging reconstruction, okay, but we want to measure how close we can get from the real positron annihilation position, okay? So you're going to do the photon tracking or positron tracking, let's say. So to the definition of resolution with this simple case, we have the following. So you have the photon coming here, there is a Compton scattering happening here, but still this is the original line of response that you get from this photon, okay? The photon scatters, here there is another Compton scattering, maybe with a pixel hit, and then it goes down. And in fact, this Compton, the electron that was generated by this Compton emitted a second photon from bremsstrahlung, and then it went up, that maybe there is a pixel hit there. What we call residual now would be the distance in the plane of detection, okay, from the pixel hit to the original line of response position. And this is what we get. The different curves here is for the 100 microns pixel pitch with a 50 microns Kapton flex. The same thing, but for 200 microns pixel pitch. And then for 100 microns pixel pitch, but now having an absorber layer in between, okay, to increase the efficiency. And what I have seen is that 90% of the hits in the line of response that we measure are within 200 microns of distance. Okay, you see that if you change for 200 microns, this changes about 1%. So this could help us a lot in power consumption, for example. We change the number of channels, and this will change the power consumption. And then we see that if you have the bismuth, this gets reduced in this case. But the interesting is that the efficiency grows from 30 to 45%, okay? And then you have to square this for the 2 photons coincidence. But you see it's a trade-off between resolution and efficiency. So we are working on this to see what is better for our imaging techniques. Then, this was a single photon source, a single tower, tracking the kind of the endpoint, one of the endpoints of the line of response, okay? After doing this, we are simulating the full scanner now, okay, so you see the 4 walls. Yeah, we are still doing a simple case to understand the physics. So all the positrons are being emitted from 0, 0, 0. The photons being from 0, 0, 0, back to back. They must hit opposite sides of the scanner. So when I check my data, I try to avoid any ambiguity that I could have. Still, you can see that there are some Compton photons there. So what we are doing is the following. So back-to-back photon for the positron annihilation, a pixel hit, detected if the world is beautiful, you know, you have the photoelectric interaction with a pixel hit in both cases. We have a line of response, and then we measure the distance. This case would be 0, very good. But world is not beautiful, so what happens a lot is a Compton scattering, for example, and let's say there was no pixel hit on this case. Let's say this photon propagated further. This would be the line of response that we calculate. In fact, coming from the same photon, this would be a bad line of response, and this is the residual that I'll show now. Okay, so this is the result. Again, so having the full scanner, okay, we can have vacuum or water here. So this is what I'll show. Having 100 micron pixel pitch without water in the center, we measure that 78% of the lines of response that we reconstruct are within 200 microns of positron decay position, positron annihilation, sorry. If we add water, so this goes to 61%, but there's nothing we can do there. The water is like a body volume, right? And if we add the bismuth as absorber layer, we see that the difference is not as high as before for the single wall case, okay? So the bismuth added reduces about 7%, but while in the two photon detection efficiency, we get 11% increase, okay? So very good. Where this put us in that overview of the resolutions, we are here now. So from TTPAT to, again, still the cylindrical geometry, but 100 micron pixel pitch, we gain in resolution, but we keep the efficiency, of course. And now with this new scanner design, we go from, sorry, I have to see here, I think 6 to 9%. No, it's not right. Yeah, 6%. And if we add the absorber layer, we can reach 14% of two photons detection efficiency, but with the payoff, trade-off of the resolution that we achieve. Okay? This is in the simulations now, just to show you, we are developing the detector for this scanner. So we have the H2020 Monolithic ERC project. Again, check the poster, please. And then basically, we're developing Asics for different R&D projects with hexagonal pixels of 65 microns width, which is equivalent to 100 microns in X and Y pitch. We have been testing this chip in SPS. You can see the efficiency here. We are achieving above 99% detection efficiency. And the timing resolution, though we are still not planning to have timing resolution on this PET scanner,